if we draw a smooth curve on the plane like this one in green here, and we connect its two endpoints with a line like this one in blue here, is it always true that there will be points on this green curve such that their tangent lines are parallel to this blue line? In this case here, we have this point, and this point, such that if we draw their tangent lines, we can see that they're all parallel to the blue line. But is this true in general? This is the content of the mean value theorem, and it states that if we have a function f from the closed interval from a to b to the real numbers, and if f is continuous on this closed interval and differentiable on the interior of this interval, then there exists a c in the interior of this interval such that the derivative of f at c is equal to the slope of this line that connects the endpoints of the graph of f. And so let's prove this result. So first we have to show the particular case where f of a equals f of b. So this will correspond to a graph of f whose endpoints are at the same level. So the line connecting them is just a horizontal line. And we know that continuous functions on closed intervals must admit a maximum and a minimum point. So this is just Weierstrass's theorem. And if the maximum and a minimum of f are located at the endpoints, so a and b, then f must be constant. And then we're done because the derivative of constant functions is just 0 everywhere. So otherwise, f has a local maximum or a minimum for that matter in the interior of the interval. And it's not hard to show that the derivative of f at this point, at this maximum or minimum, is 0. And I left a hint here if you want to prove that yourself. Okay, so to conclude this proof, we have to show the general case. So suppose that f of a is not necessarily equal to f of b, and we define the function g of x, which is equal to f of b minus f of x minus k times b of x, where k is defined by this term here. And now you can note that g of a is equal to g of b, which is equal to 0. So we can apply the particular case we just showed, which immediately gives the result. And I encourage you to check this for yourself. All you have to do is calculate the derivative of g with respect to x. And as a bonus question, can you see why the hypotheses that f is continuous, f is differentiable, and that f is real valued were all necessary? So I'll give you the answer in 3, 2, 1.